So today we are going to be learning how to figure out the whole balancing mechanism. First of all, we'll try and understand why is balancing necessary, yeah, which we already done in class. By this actual practice, we will see that the smallest unit that takes part in a reaction, as you guys remember, is what? Since I've said as you guys remember, you have to give me the correct answer. Atom, exactly, atom. But what we balance over here, let's see if our theory matches with what we're going to do. So as you can see, there are three things on the top. Make ammonia, separate water, and combust methane. We'll work with the ammonia reaction today in both the sessions. The left hand side is the reactant side, the left black window, the right black window, the small window is the product side. All right. There's a display control. I can mess around with this. At this point, I will not do anything, but yeah. So I'm going to change this to balance scales. Okay, so this is just like a yeah, it's going to tip over. You'll see what happens very soon. This is just nitrogen and hydrogen. So clearly, we are actually balancing atoms. Do you guys see that right away? Here you have N and there's H over here. So it seems like we are balancing atoms, but what you have in actual reactions are molecules, right? That's the mess up. That's why you need this balancing business. Yeah, exactly. Because I want to balance atoms, that's my own thing. But in nature, stuff exists as molecules. We learned that in the last lab, remember? We saw that hydrogen cannot exist as an atom because it has only one electron and its shell can accommodate two electrons. So it's unsatisfied and it bonds with another hydrogen atom and forms a H2 molecule. Similar story with nitrogen, slightly different, but basically the idea of unfilled unfilled shells. Yeah, a little bit of a revision. Is everyone on the same page with everything that I just said? Yeah, we did oxygen, exactly. We did hydrogen and oxygen. Okay, so on the reactant side, which is the left hand side, I'm going to change this hydrogen coefficient, make it 1. As soon as I do that, you see that this balance tips to the left, and well, there's hydrogen on the left hand side, none on the product side. So clearly over here, the left hand side is the reactant side on both the N and H balances. You can't hear me? How about everybody else? Can the rest of you hear me clearly? Okay, maybe an issue at your end, Arjun. Maybe an issue with your internet. Alright, moving on. So what we have done is we have placed one molecule of hydrogen on the reactant side. That's what I've done. Yeah, I paused. I didn't talk. So, yeah. Okay, anyway. So, this is an important thing. Why are we increasing the number in whole numbers? Why am I going from 0 to 1? Why can't I make it 0 to 0.5? Can I do that? Or is that not okay? You can see that if I do this, it only is adding in multiples of 1. Why can't I add 0.5? Think, guys, give me an answer. Why are whole numbers needed? Why can't I have 0.5 H2? Jacob, I think yes, you can't have half a molecule. Yeah? Did you guys understand what Arjun just said? It is true that the smallest reacting unit is an atom, but in nature, hydrogen exists as a molecule, and I cannot really have half a molecule. Yes? Does that make sense? So, in a chemical reaction, you take some reactants and put them together. You take the reactants as you find them in nature. Hydrogen is found as a molecule, not as an atom. Okay? So, you're forced to increase the quantity by one molecule and not half a molecule or one atom. Is this clear? Is this idea clear? Okay, excellent. So, you can see in the balances that hydrogen is, well, unbalanced clearly. Nitrogen is balanced because I haven't added anything. So, I need to add more hydrogens to the right hand side to try and balance the scale. So, I increase this number by 1. Now, as soon as I do that, you see that, okay, both the scale now are unbalanced. So, I'm trying to balance it, but, well, not so much. But this is the exact same thing that the guy weighing your vegetables does. Yeah, he adds stuff on the left hand side and the right hand side. He's a little bit more expert than we are at this point, so he does it really quickly. We are going to do this slow and steady so that you guys understand what's going on. Okay. So what has happened here is, on adding one molecule of ammonia, I've added. You see the scale of nitrogen has only increased by 1 on the right hand side, and there's nothing on the left hand side. Yes, this makes sense because I haven't changed anything. The important thing is that hydrogen is found in the bonded state with the nitrogen atom. Hence, just by increasing the number by 1, I've increased 3 hydrogen atoms. Hence, it right away outbalances the 2. Yeah, it is heavier than the 2 atoms. Is this idea clear? So this is consistent with our understanding that hydrogen atoms can't really exist on their own. They have to be bonded, whether with another hydrogen atom or in this case with a nitrogen atom. So now everything is unbalanced, so I'm going to have to obviously change a few other numbers. I'm going to increase, well, the most logical thing that seems to be plausible is I increase the nitrogen balance, the N2 to 1. Okay. Now, again, since nitrogen is found as a molecule and not as an atom, right away I have 2 atoms on the left hand side, which again disbalances the scale. Is this okay? Again, this is consistent with our theory that nitrogen also cannot exist on its own. It exists in its bonded form, which happens to be with another nitrogen atom on the left hand side and with 3 hydrogen atoms on the right hand side. So that is consistent with the idea that nitrogen atoms cannot exist singly. Cool? So what we have done is, because we've added one molecule of nitrogen on the right hand side, it obviously amounts to 2 atoms, and this is why the whole thing is disbalanced. So what do I do now? This is a pro tip. This is a bit of something that you will realize if you balance a lot of reactions. It helps to balance hydrogen and oxygen in the end. Okay. First, let's focus on everything else. So at this point, let's try and balance out the nitrogen first. How do I balance out the nitrogen? Can you guys tell me? What do I do? Tell me, add 1 to the left, or add 1 to the right, or add 2 to the right, or whatever, in that way. So that's the format of the answer that I'm expecting. Can you guys tell me how can I balance out? Exactly. Okay, great. Now I have nitrogen balanced out. Now I'm left with unbalanced hydrogen atoms. That's easy right now, right? All I have to do is I have to change this number on the left hand side and everything should be balanced. What do I do to this hydrogen now? Yep. There you go. The simulation is happy and we are done with this. Cool? So this is clearly the complete balance equation. There are 6 atoms of hydrogen on the reactant side and 6 atoms of hydrogen on the right hand side, and we already balanced nitrogen. Okay. So now what I just said, it seems like I have in effect actually balanced the atoms. Yes? So the initial hypothesis, or the initial thing that I told you guys in the theory classes, that atom is the smallest unit that takes place that takes part in a reaction. That's consistent here because the balancing actually is atoms. Although we have to, because of the way nature works, we have to figure out the molecules. But essentially, you are balancing atoms. Is this concept clear? This is extremely important. Okay, excellent. So clearly, total mass on the reactant side is mass of 6 hydrogen atoms. Yeah, 3 into 2 plus the mass of 2 nitrogen atoms, which is 1 into 2. Agreed? 6 hydrogen atoms and 2 nitrogen atoms. Similarly, the mass on the product side is 6 hydrogen atoms and 2 nitrogen atoms. So this is simply a reflection of the conservation of mass. Done? Understood? Okay, I'm going to pause this recording. We're going to go to class actually now to understand a few very, very cool ideas. Yeah, this is a very small part. Just hold on. Alright, so we've just figured out the law of mass action and also the law of constant proportions. Yeah, those two things were what were made clear from that earlier explanation. Here, this is a very interesting lab. You guys can mess around with this. Both of these labs also had a game where you can, test your skills, so to speak. We are going to focus on real reactions and not the sandwich shop. You can also mess around with this. I'm going to make ammonia again because that's the reaction that we just studied. The balance reaction is given to you. We've just balanced this. Again, black window left hand side is reactant stuff. Reactant side, and the right hand side is the product side. Everything else here, these are the number of reactants, these are the number of products. Okay, cool. Okay, so what I'm going to do is I'm going to increase the number of molecules one by one. Okay, let's first increase nitrogen. So one small thing, the left and the right windows now refer to before reaction and after reaction. Strictly speaking, it's not the reactant side and the product side. It's trying to say that if I dump these things inside a beaker and let enough time pass, what will I have left? Do you guys understand that? So loosely speaking, I could call it the product side and the reactant and the product respectively. But actually it means this. Before reaction, I take a beaker, I dump in these things. After reaction, I let enough time pass and I open the beaker and see, and this is what is there on the right window. Okay? Is that alright? So, clearly if I just add one nitrogen molecule, I've added hydrogen, my bad, one moment. Let's add nitrogen. Okay, I've added one nitrogen molecule, nothing happens. Nitrogen exists as itself before and after reaction. Yeah, since there's no hydrogen, obviously there's no ammonia that's going to form. So clearly I need to add hydrogen atoms. I can't add atoms without adding molecules, so I will add an entire molecule. Now this is interesting. Nothing happens. Why is that? I have hydrogen and nitrogen, but still there's no reaction. What happened here? Any ideas? Arjun's correct. Jacob, I would say that nitrogen is excess. Be careful about the word excess. Excess is very easy to understand. At this point, let's not talk about excess. Yeah? Yeah, it's correct to say what Nandan is saying is correct. The idea of excess and less, excess just means more. There's nothing extra here, right? Both things, it's easier to say that hydrogen is less. It's a little bit more difficult to understand that nitrogen is in excess. Okay, do you follow what I'm saying? So the idea of what is excess and what is less is relative. Did everybody else understand what I just said as well? That's extremely important since he brought it up. I wasn't going to talk about excess and less. Well, I was going to later on, but since he brought it up right now. Clear? There's clearly a deficit of hydrogen. There's not enough hydrogen. So, according to the balanced equation, I need 3 molecules. I've just supplied 1 molecule. Even if I increase it to 2 molecules, nothing's going to happen. Yeah, let's see. There you go. As we have understood earlier, nothing's going to happen. So I need exactly 3 molecules of hydrogen for it to react. Now, is that idea okay? So if I add the third hydrogen, straight away I get 2. Pretty interesting, right? You don't get one ammonia. You just get 2 right away. This is okay? So this is a very, very hypothetical picture, right? Because although we have understood this is mainly to understand the idea of what is more and what is less. Strictly speaking, obviously you don't have one molecule reacting. You have like billions and billions and billions of molecules reacting. So as soon as you put in nitrogen and hydrogen, you will get ammonia depending on the condition. There are some other things that come into the picture, which you guys will probably learn the next year. But this is a very simplified picture to explain the idea of excess and what is less. Clear? Okay, now I'm going to just hit reset all and take another example with the same ammonia setting. I will start with 2 molecules of nitrogen and 4 molecules of hydrogen. What do you think is going to happen? Predict it, and then we'll see if you guys. Yes, this is called the Haber's process, Jacob. Well, the Haber's process is a very specific process where you have to have this particular pressure, this particular temperature, and also some other things dumped in. So it's a very specific process, but in general, ammonia is formed using the process just mentioned by you. All right, that's the industrial way of producing ammonia. It's very useful because ammonia goes into making fertilizers and a lot of other stuff. Okay, back to the class. If I put in 2 molecules of nitrogen and 4 molecules of hydrogen, what is going to happen? Predict, please. Okay, Arjun says that. Arjun says only 2 molecules of ammonia will be formed with excess nitrogen and hydrogen. What do the rest of you guys think? Do you guys agree with them? Do you guys disagree? What's your what are your ideas? You mean H2, right? There is no O2. I'm guessing that's a typo. Jacob? So it seems like you're agreeing with Nandan. What are you saying? I just see you writing N2. So what's N2? So Jacob and Arjun seem to be agreeing with each other. What are you saying, Nandan? What do you think? Okay, cool. So everybody seems to be agreeing, which means you guys have understood this. Excellent, very good stuff. Let's see. I've added 2 molecules of nitrogen, 4 molecules of hydrogen. 1, 2, 3, 4. There you go. As you guys predicted, exactly that has happened. Clearly, I've added a little bit more than 3 hydrogen atoms, but I need 2 more hydrogen atoms to have complete reaction. Yes? So both products, both reactants, nitrogen and hydrogen, are left over at the end of the reaction. You guys understand this? You guys have all predicted it, so I'm guessing it should be easy for you guys to figure this out. Since for each molecule of nitrogen, we must have 3 molecules of hydrogen. Clearly, I need to increase the molecules of hydrogen to 6, and then everyone's happy. The exact number of ammonia molecules formed. So this is another characteristic of a balanced equation. Reactants are present in the right. If the reactants are present in the right proportions, there are only products left, and there are no reactants left over. Clear? Alright, that was it with the simulation part. Let's get back to class.